Okay, so in this video, now I'd like to discuss the idea of topicity and chemical equivalence, okay? And topicity is going to tell us about the relationship and the both chemical and magnetic equivalence between two indicated groups in a compound. And this type of question on an exam is most similar to questions from Orgo 1, where you were asked to decide what is the stereochemical relationship between two compounds. Here we're looking at two groups within the same compound. So those groups may be homotopic or enantiotopic. And homotopic and enantiotopic groups are always chemically equivalent groups. And that means they have the same chemical shift on a proton NMR because they are in the same electronic environment. Diastereotopic, which always means non-equivalent, but it's a special type of non-equivalent, and simply non-equivalent, okay? These refer to either a stereochemical difference between two groups or a structural difference in terms of constitutionality or how the sigma and pi connectivity is put together. They are ways to describe chemically inequivalent or non-equivalent groups, such as hydrogens. And chemically non-equivalent groups are going to have different chemical shifts. And identifying groups according to their topicity is very important for counting numbers of unique protons in a molecule in terms of what would be expected on an NMR spectrum. So when I'm doing problems where I'm asked to decide between these four options, okay, I know that if the two groups are chemically equivalent, then it's going to be either homotopic or enantiotopic. So I decide that first, and it gives me a 50-50 shot. If I decide that the two groups are chemically non-equivalent, then it's either diastereotopic or it's structurally non-equivalent. So let's go through some examples. That's the best way to approach this. First, checking out the two protons here. They are on the same carbon. This is carbon 3. So they are structurally equivalent. They are the same distance from all other atoms in the molecule. And one hydrogen is forward, this one. The other hydrogen is back, that one. However, there is nothing on the front face of pentane that makes it different from the back face. And therefore, there is no stereochemical difference, or the wedged hydrogen does not see anything differently compared to the dashed one. So they are also stereochemically equivalent. So I know that it's either going to be homotopic or enantiotopic, because these two protons are completely chemically equivalent. And replacement of one proton with some other atom is a way of doing a test to see the relationship or the topicity. So I'm going to replace each proton one at a time with deuterium, but this is a fictitious test, and you could use any atom you'd like besides hydrogen. We're trying to see if this carbon becomes a stereocenter. However, this carbon is still achiral because it still has only 3 unique groups. The ethyl groups are the same. And these two groups, these two molecules, I shouldn't say two, they are the same molecule. They are identical. If you just take one of them and flip this over, okay, you'll see this compound, right? These two compounds are superimposable. So if the two isotope replacement structures end up being identical or superimposable, that means the groups that were replaced are homotopic. And those two hydrogens would show up at the exact same chemical shift on the NMR. Let's look at another example. Now focusing on this carbon, okay? It has a methylene pair of protons, and those protons, once again, appear to be structurally equivalent because they are on the same carbon. They are both one away from nitrogen. They are one away from CH2, okay? They're the same distance from everything. Also, they are stereochemically equivalent because, yes, one of them is forward and one of them is back, but there's nothing on the front or back face that distinguishes the front from the back. There's no difference in the two faces of the molecule here, and there's free rotation. So if I replace the wedge hydrogen with deuterium as compared to doing the opposite substitution, we do this time generate a new chiral center where this carbon now has 4 unique groups bound. Nitrogen, heaviest, priority 1, carbon, priority 2. Deuterium is an isotope of hydrogen that weighs 1 AMU more, so it is priority 3. So this one has the clockwise configuration, R, where the lowest priority is back, and that's correct. This one appears to be clockwise, however, the hydrogen, number 4, is coming at us, so we must flip the answer. It's really S. And for two compounds that have opposite configuration at their only chiral center, they are enantiomers, or non-superimposable mirror images, which means these two protons that were replaced are enantiotopic. So they're still chemically equivalent. Those two protons still show up at the same chemical shift. They happen not to be magnetically equivalent, but we're not going to dive into that in this course. So now we're going to introduce some more asymmetry with this pre-existing chiral center here, where we have the S configuration. So this time, the protons that are indicated, they are structurally equivalent because these two protons are on the same carbon. They're one away from methyl, they're one away from the alcohol, and they're the same distance. However, their stereochemistry is not the same. They are stereochemically non-equivalent. Here's the reason. One of them is coming forward. So replacement of that proton with deuterium will produce one isomer that is not a mirror image, nor is superimposable with the other replacement structure. We have the fixed chiral center that we said was S. That's not changing. We also have a new chiral center. You could prove that this is also the S configuration in the top compound, and then it switches to R. So these are not the same structure because R and S swap, but not everything swaps, right? They are not enantiomers, but instead they are non-superimposable. So they are stereoisomers, but they're not enantiomers, therefore they are diastereomers, right? Or something changes, right? S changes to R, but at the same time, another stereocenter stays the same. S remains S. So these protons here were diastereotopic. And in fact, every CH2 or methylene like this will be diastereotopic if there is a single chiral center, just one, in that molecule. Because the front face has the hydroxyl, okay? And this hydrogen here is also closer to the hydroxyl in space, or it's gouged to the hydroxyl, whereas the other hydrogen is anti. So they have different dihedral angles relative to the hydroxyl, and therefore they are stereochemically non-equivalent. So diastereotopic is best summarized as being protons that are the same distance from all other groups or structurally equivalent, while having some spatial difference, or three-dimensionally, these protons don't see the two faces of the molecule in the same way. One of them sees the alcohol. That's the one that's gouged to it. The other one does not see the alcohol because those groups are anti. Let me show you some more examples of diastereotopicity. We take these two methyl groups. We can compare methyl groups. We can compare any two groups. It's not just a rule for hydrogens. If you're comparing the methyls, it's simplest just to replace all three hydrogens, CD3 on top, or you could have CD3 on the bottom. So here, there's a pre-existing chiral center that is in the R configuration. And we've generated a new chiral center, okay? And that is in the, what is S, and now has switched to R. So once again, we have two diastereomers of one another, where R stays R, so some stereocenter does not change, and the other S switches to R. So these are diastereomers, which means those methyl groups were diastereotopic. Once again, they are structurally equivalent because the methyl groups here were on the same carbon atom and the same distance from bromine, etc. But one of them is always cis to the bromine, while the other is always trans. So there's a cis-trans difference between those groups. When it's only a cis-trans difference and nothing more, the groups that are indicated are diastereotopic. Another example. These two protons, one is cis to the aldehyde, right here, and the other is trans. And this is a ring, just like the previous example, so it's rigid. Or these bonds cannot rotate. So the aldehyde's on the front of the ring, and that causes the two faces of the ring to be different. In other words, replacing one proton with deuterium is going to produce a different stereoisomer compared to if we replace the other proton. This is the cis isomer, where deuterium and aldehyde are on the same side, and this is the trans isomer. Now these compounds, cis and trans, are always diastereomers, right? Because I kept the aldehyde forward and I swapped the deuterium from front to back. But there are no chiral centers in this molecule or these molecules, because the carbon that we did replacement on lies along this plane of symmetry. So it cannot be an asymmetric center if it lies along a plane of symmetry. So these are achiral or diastereomers that are geometric isomers. However, the protons are still diastereotopic. One of them sees the aldehyde and one of them does not. They are both 1, 2 carbons away from this aldehyde, the same distance. There's simply a cis-trans distinction. In the next example, I'm going to now compare these two methyl groups that are on an alpha-beta unsaturated ketone, and we'll see an analogous geometric isomerism. where replacement of one methyl with CD3 generates one stereoisomer, where here CD3 and ketone are cis to one another. That's known as the Z isomer when they're on the same side of this pi bond. Remember that pi bond is rigid and cannot rotate. Replacement of the opposite methyl group produces a different stereoisomer, where now the high priority ketone and high priority CD3 are across the alkene or trans to one another, which means that is an E olefin. So E and Z, okay, just like cis and trans, are diastereomers, but there are no chiral centers. There are no carbons that have 4 unique groups bound. So the methyl groups here are still diastereotopic. Okay. So really common places where you'll see diastereotopic protons are on rigid rings, okay, and on alkenes, terminal positions. The final type of topicity is comparing two protons that are just structurally non-equivalent. So let me show you what that replacement test leads to. So perhaps we could call this isomer the 1,2 deutero, where it's adjacent to the oxygen of that lactone. And the other isomer, we'd have to break a sigma bond or two and reconnect. Now the oxygen and the deuterium are 1,4. In other words, these two compounds are structural isomers. Or constitutional isomers of one another. So if you have to break a sigma bond and reconnect the atoms in a different way, okay, then they're simply structurally non-equivalent. So use those types of topicity to understand the number of unique protons in a molecule and to be able to predict the relative chemical shifts of protons based on their proximity to pi bonds and electronegative groups. For more practice on topicity, you can visit the multiple choice, specifically in Unit 1 of my Orgo 2 course guide at chemguides.com.